In this video, we're going to discuss bearings and how to size them and how to design them. Before we can begin, we need to set some definitions about what a bearing is. A bearing is any two parts that have relative motion to each other, and we classify bearings in several different categories. The first one is a plain bearing. A plain bearing has two materials that rub directly against each other. There's several different examples. So typically one part is structural material like a steel or a cast iron, and the other part is a bearing material, and it's supposed to be something that won't wear out and has very low friction. So bronze is a good example. Or there's a material called babbitt that has tin or lead infused in it that makes it very slippery and lots of friction and low coefficient of friction. Plain bearings are typically custom designed for each individual application. Within the plain bearing category, there are bushings, which are radial plain bearings. So the only thing they're allowing is rotational motion, and they're a complete closed cylinder. Thrust bearings support axial loads entirely. And then journal bearings is when a shaft rotates freely in a supported sleeve or shell. So maybe this goes all the way around to be a complete cylinder, but very often it doesn't. And very often, especially in the journal bearing, there's some sort of lubrication that's occurring in the bearing to allow the journal to rotate freely. The other type of bearing that we consider is a roller element bearing, and these are almost always composed of hardened steel balls or rollers, and the rollers are captured between hardened steel raceways, and the translation of motion comes from rolling, so you get the effect of wheels working to reduce the friction. These are very rarely designed custom for an application. Much more often, these are selected from manufacturing catalogs, and they're made in large bulks, and you purchase the type that fits your application. So a plain bearing, you're going to design the bearing to match your shaft, and a roller element bearing, you're going to design your shaft to fit a particular bearing. Roller element bearings can support all kinds of different loads. There are different types of roller element bearings, and we'll talk about several common styles for supporting radial loads or thrust loads, or combinations of radial and thrust loads. I think it's really important as we consider this to realize the understanding of what a bearing is really doing. And this is Anthony G.M. Mitchell is a major bearing designer. He had a lot to do with the construction of journal bearings and all that they do. And this is what he had to say. To the machine designer, all bearings are of course only necessary evils, contributing nothing to the product or function of the machine, and any virtues they can have are only of a negative order. Their merits consist in absorbing as little power as possible, wearing out as slowly as possible, occupying as little space as possible, and costing as little as possible. So that's a good thing for us to understanding. Having a good bearing doesn't increase our power production or anything like that. It stops the decrease of our power production. It's a good perspective to have. Now, looking at different types of bearing material, here's some just examples of different types of babbitt and how hard they are and the type of where they would be used. Okay, so let's look at three different types of lubricated plain bearings. So lubrication is absolutely the key to reducing both friction and wear. And in hydrostatic lubrication, you have a continuous supply of a high-pressure lubricant and a very low coefficient of friction. Actually, for zero relative velocity, if you're moving very slowly, the coefficient of friction is almost nothing. And with a relative velocity, it's normally around 0.002, which is a very small coefficient of friction. Hydrodynamic lubrication is there's enough lubricant to allow the moving surfaces to actually pump the lubricant between the surfaces. So there's a dynamic film of liquid. In other words, if I stop the rotation of the shaft, the film disappears from between the shaft and the bearing. But as I spin the shaft, I'll force a film in between the shaft and the housing. This means when everything is stopped, wear could occur. So wear only occurs during startup and shutdown. So this is why you do eventually have wear in a car engine, for instance. Everything is perfectly fine as long as the car is running, but during the startup and start down, you might be tearing up your journal just a little bit as you start. And then the last one is elasto-hydrodynamic lubrication. So this is specifically used to lubricate things like gear teeth or cams, anything that's going to have a point contact. And so if you have a point contact, all of the force has to be distributed into practically no area. So you have to have some sort of deformation. When that deformation occurs, you have some local deflection, and this patch where the local deflection occurs is where the film can develop. So even though you don't have film on most of the contact, you will develop a film exactly where the deflection occurs. Here's an example of a hydrostatic example. The best example of this for practical life might be some of the domes for stadiums are rolled out and on using hydrostatic pressure. So you're going to pump enough pressure into it to actually float the entire roof on a thin film of oil, and then you can slide it with very little work once you get it going. Elasto-hydrostatic, again, there's gears and cams, and the figure 11.2 shows you that as your speed increases, you get closer and closer to a full film lubrication. And so there's actually a perfect spot of relative velocity that you're going to get a full film and slow velocity, and you're going to have the least amount of friction. And so that's what we'll design for. We will not discuss elasto-hydrostatic friction in this course. What we'll spend the rest of this lecture discussing is hydrodynamic friction, and this includes journal bearings. So figure A shows a shaft resting in oil without the shaft spinning. As the shaft begins to spin, notice that it moves to the right as we're looking at it during the startup. So now we're going to start having boundary lubrication, and the contact point leaves the center line. It leads the center line, meaning it's in front of it, and it also is no longer on the center line. As omega increases and you get enough speed, you'll actually start pumping oil inside, right here. Now there's oil getting pumped inside between the bearing housing and the journal. And this is going to allow the entire journal to float, and now the shaft is going to follow or lag the center line of the housing. So there's a lot of work that's gone on to model exactly how this happens, and the key thing we want to do is decide what type of tolerance we want right here, and that's going to be highly dependent on the speed of the shaft. So we need to know the speed of the shaft. We need to know the forces generated by the friction of the lubrication as it drives itself under the shaft, and all of that's going to help us to dictate what type of lubricant we should use, what type of tolerances we should have on the shaft versus the housing, and how everything ought to work together. So here's another example. During the process, there's going to be some place where we have a maximum force and a minimum thickness. So as we look here is the minimum thickness of the lubrication, here's the maximum thickness, and this is some starting angle, and we're going to figure out exactly where the highest and lowest pressures and everything else goes. Notice while we're at this diagram, we also can see the eccentricity of the journal in relation to the bearing housing. And obviously that has something to do with the clearance. So for any particular point, I can find what the velocity of the fluid is. The velocity of the fluid right here is 0, it's stationary. The velocity of the fluid right here is the speed of the journal at that location. Those two changes in velocities help me understand forces, and that's going to be how we're going to generate the force that the lubricant exerts onto the journal. This is a graph that shows how P moves as a function of theta. So we're considering running, and now we're going to say theta is equal to 0 when we're in line with the eccentricity. In other words, the shaft, if I were to draw a line from the center of the shaft to the center of the housing, that's going to be my theta is equal to 0. And we can see that there is a location, there's a theta max that produces a P max, which is the maximum force being exerted on the journal. And we also can see across the width of the journal that the maximum P is exerted right there in the middle. This is going to help us find the maximum pressures, and that's what we're looking for. Alright, so here's the steps to design a hydrostatic bearing. Usually I already know the forces that need to be on the shaft and the rotational speed of the shaft. What I'm looking for are diameters and clearances. So I'm going to start with making a random selection, and then I'm going to use that to calculate in order the viscosity requirements. That allows me to choose a lubricant. Then I'm going to find the average pressure. I'm going to find the location of the maximum pressure. Then I'll find the maximum pressure. Then I'll find the angle of torques to the applied load. Then I'll find stationary and rotating torques, calculate the power loss, and calculate the coefficient of the bearing. So just so you know where we're going, and then that gives me the minimum film thickness, and finally I can have a factor of safety to make sure that my film never gets too thin and we don't wear out the part. So this is what we'll do. What I'm going to do in the next few slides is discuss how to find some of these, the maximum pressure, and then in class we'll go through an example where we do all of these steps in a specific design scenario. Obviously when I make my random selection I won't be right yet, so after I get my factor of safety then I'll have to iterate and go through again probably at least a couple times, if not many times, to get to the right answer. So going back to the beginning, usually the applied force on the shaft and the rotational speed of the shaft are known. So the first thing we're going to do is define a dimensionless parameter. We'll call it K epsilon, and it is a function of P, which is the resultant force. That's something I know. The clearance diameter, that's the maximum amount of clearance. This is, again, something I know. The maximum clearance between the shaft and the housing. I need to find the absolute viscosity, which is the kinematic velocity times the mass density. This is something I'm going to make a decision about, and we'll look at a chart to show you how to make that decision. Then I'm going to find the speed of the journal, and this N prime is in units of revolutions per second. So we'll translate anything we have from revolutions per minute into revolutions per second. And then two more, the length of the bearing, which is L, and D is the diameter. And all of those, and then we need, all of those will help me know this dimensionless parameter, this K epsilon. Once I know that, I'm going to find an Ockvik number, and the Ockvik number is a function of this K that we just found. And from that I can get the average pressure. This is a design decision, and I'll talk a little bit more about it in the next couple of slides, but typically I'm going to say I desire a particular Ockvik number. And once I've found, so I'm going to find viscosity specifically. I'm going to choose the correct viscosity and clearance difference to allow the Ockvik number to be where I want it to be. And maybe this equation does a better job of even showing how that ought to happen. If I change the D over L, that's going to influence the Ockvik number. If I change CD over D, that's going to influence. So these ratios are really what's doing the influencing of the Ockvik number. Now, this is, epsilon is the eccentricity ratio of the shaft to the bearing. And it's a function of the Ockfick number. Matter of fact, that's really what we're trying to describe with the Ockfick number. And this equation, if you look at it, very clearly looks like something that's been curved fit. And it has. This is the experiential number. This is curve fit based on existing data of how things have actually happened. We do have a theoretical number, but since the theoretical number doesn't quite match reality, in this course we're always going to use this number, this approximation using the Ockfick number to calculate our eccentricity ratio. So let's take a look. Here's the Ockfick number as it goes from 0 to 100. Here's the theoretical curve. Here is the experiential curve. This is the one that had the log in it. And these are data points of where things seem to fall. So the experiential curve much better matches reality. Also, we can look at how the Ockfick number is influenced by P max over P average and the ratio of the torques. So here's the experiential, there's the theoretical. So there seems to be like there's still a ways to go in the theory behind the Ockfick number. Again, the larger the Ockfick number, the more shift we're going to have in theta. Here are the guidelines. If we have a moderate loading condition, then we're going to aim to have an Ockfick number less than 30. If we have a heavy loading condition, we're going to aim for the Ockfick number to be less than 60. And if we have a severe loading, we'll aim for the Ockfick number to be less than 90. As I said before, there's a lot of steps to go through here, and this is best shown using example. So in class, we'll start with these